So let's move over to the main title in the OGM, which is the Clarke Medal presentation by our Society's 2019 winner, Professor Dietmar Müller. Several factors, including the pandemic, conspired against us having Dietmar receive his medal and give his presentation. The Clarke Medal, as many of you would know, is the Society's oldest award. It's named in memory of the Reverend William Brandlight Clarke and the field in which he worked. He was an eminent geologist and an important figure in the foundation of the Royal Society of New South Wales. The Clarke Medal made the Society the first colonial society in Australia to reward scientific achievement. The first medal was awarded in 1878 to Professor Richard Allen of the British Museum, famous for his studies of Australian vertebrate fossils. In 1879, it was awarded to George Benton of the Royal Botanic Gardens in Kew, who made a major contribution to the study of Australian flora. And in 1880, to Thomas Henry Huxley of the Royal School of Mines in London, for his valuable contributions to the knowledge of the natural history of Australia. Many of the medals, fortunately, since then have been awarded to people resident in Australia. The first Clarke Memorial Lecture, the tour emerged subsequently in the medal lecture, was delivered on the 24th of September 1903 by geologist and Antarctic explorer, Professor Edgeworth David. His address was entitled The Life and Work of the Reverend W.B. Clarke. Another Antarctic explorer, Sir Douglas Mawson, delivered the lecture in 1948. This brings me to Professor Dietmar Müller, geophysicist from the University of Sydney and our 2019 winner. Dietmar's primary research focus is the physical fabric of the world and how it has evolved over more than 1 billion years, reaching back in time to a time when life as we know, of course, did not exist. In one of his most exciting projects, Dietmar and his team used big data analysis to build the first digital map of the age of the world's ocean floor. His lecture tonight is entitled Reconstructing Ancient Oceans, Sea Level Fluctuations, and the Deep Carbon Cycle of Biodiversity. Relaying the long version of Dietmar's bio would consume all the remaining time we have tonight. In short, he received his undergraduate degree from the University of Kiel in Germany and his PhD in Earth Science from the Scripps Institute of Oceanography at UC San Diego in the US. We are most fortunate that Dietmar accepted a job at the University of Sydney in 1993 and stayed, I think, for love, Dietmar, correct? Here he has built the EarthByte research group pursuing geodata synthesis through space and time. He leads the construction of the virtual Earth laboratory that is assimilating the wealth of disparate geological and geophysical data into an experimental planet. Professor Müller held an Australian Laureate Fellowship from 2009 to 2014 and is a fellow of the American Geophysical Union and the Australian Academy of Science. Dietmar, as a winner of many awards, I trust that you are especially proud to receive the Society's Clarke Medal and deliver the Clarke Lecture tonight in honour of a key figure in the life of the Society. You rightly join an illustrious lineage. Would you please come to the stage to receive your medal and certificate and deliver your lecture? Yeah.
So today I'm going to talk about reconstructing ancient oceans. Now this is an introductory slide. It's about my EarthByte group. As we've already heard, really our specialty is building an experimental planet through a combination of open software and open access data and models, and trying to understand how the Earth has evolved over geological time. And today we're going to stretch this experiment back to 1 billion years before present. Okay, so this is a Columbus view of the Earth, with the continents and the oceans. And I should mention first off that there's a special word for the topography of the oceans. It's called bathymetry. Now, as humans, we're mostly focused on the continents. We live there, and of course, even though over 80% of Australians live quite close to the coast, I think generally, we know very much about what happens in the oceans. The geology of the continents has been explored for hundreds of years, while our knowledge of the oceans is really quite recent. Post-dates World War II, only through the development of modern sonar methods are we in a position to have mapped the oceans and to come to the conclusion that they are not a vast, featureless and boring bathtub as they were imagined before World War II. And so, but what makes the Earth's oceans special? Originally the idea was that they must be similar to the continents, and they're really just submerged equivalents of the continents. But nothing could be further from the truth. So what's shown here is a hypsometric curve. There are actually two diagrams shown next to each other on the lower left-hand side. So there's a histogram on the left. That's a histogram of the elevations of the Earth. So you can see this histogram has two peaks because we have fairly low-lying elevations of the continents, about 100 meters elevated. That's quite common, and that's simply because the erosion tends to flatten the continents through time. So even if plate tectonics builds large mountain chains, they don't last, geologically speaking. But there's another peak that's at 4,700 meters depth, and that's the abyssal plains in the oceans. And so the oceans are really quite different from the continents. And so that reflects plate tectonics. And so we have three histograms next to each other. On the right-hand side, there's the Earth in blue in the middle, and there's Venus and Mars next to the Earth. Now, we see that both Venus and Mars don't have such a bimodal distribution of depths as the Earth does. And the reason, of course, is that they don't have plate tectonics. It takes quite special conditions for a planet to develop plate tectonics. We're not going to get into that today, but one condition is simply the size of the planet. If a planet is too small, then the crust tends to be quite thick and unable to develop plate tectonics. Whereas if a planet is too large, then its enormous gravity field ends up squishing the crust together, and so that it's again unable to move and develop plate tectonics. That's just one of many requirements. Okay, so the oceans are systematically lower than the continents, and that's got to do with the rocks that make up the crust as well. So the continent, first of all, the crust has much lower density than the underlying mantle that's convecting like a very thick soup over geological time. But the continents are even lighter than the ocean crust, because the continents are roughly made up of granite and its various derivatives, sediments, the consequence of eroding granites, etc., whereas the ocean crust is made up of basalt. And so, using the principle of isostasy, we can figure out that the continents are much lighter than the ocean crust and much thicker, and so the continents stick out. And if you want to investigate what makes up the continents close up, take a trip to Morton National Park, for example, where you see a feature called granite faults, and that's a good representation of the geology of the continents. In contrast, I take a trip to the east coast of New Zealand. That's a place called Crystal's Beach, where my wife and I have been on holidays a few years ago now, that was before COVID. And there you find a large chunk of ocean crust that has been shoved on top of the landscape of New Zealand via plate tectonics. Now, these rocks once formed at 2.5 kilometers water depth at a mid-ocean ridge, where new crust is being generated and was abducted or accreted to the continent later. And so these are the salts. And the hexagonal patterns that you see are very typical for a cooling pattern. When these rocks cool, they end up cracking because this ends up being the most efficient way to do this. Now, the ocean floor topography is not flat as was originally envisaged, but there are great mountain chains circling through the oceans. So this is the South Atlantic view, so we have Africa on the right and South America on the left. And you see that there's a mountain chain in the middle of the South Atlantic. And that's where sea was spreading across, that's where these plates are moving apart. In this case, the African and the South American plate. New crust is being created because the melts upwelling from the mantle that when they come into contact with seawater, they cool and make new ocean floor. And so the mid-ocean ridges are generally at a depth of 2.5 kilometers, while the abyssal plains can be as deep as 6 kilometers. Now, my thesis supervisor, a guy called John Slater, who is originally from Brisbane, he taught me at the UC San Diego at the Scripps Institute of Oceanography in La Jolla, in California. So his claim to fame really is the Slater curve. And he figured out how ocean floor subsides. How does it change its depth from the mid-ocean ridge crest at 2.5 kilometers depth to the abyssal plains. And he derived a very simple formula that's shown there on the upper right. It's 2,500 meters depth, that's where it starts, and plus 350 times the square root of its age. And that describes how ocean floor subsides. So even though this was done in a fairly simple-minded way in the 70s, many more sophisticated models have been developed since then for how this works. It turns out that he was pretty close. Now, since all these detailed sonar methods were developed during and after World War II that allow us to image the oceans and figure out what it looks like today, since then we've come a long way because we've asked the question, well, what did ancient oceans look like? It turns out that this is important to know if we want to understand the long-term sea level variations, the carbon cycle of the Earth, or also the evolution of biodiversity during the last, say, 550 million years when complex life evolved on Earth. And of course, much of this life evolved in the oceans initially, and there's still a lot of biodiversity in the oceans, of course, that we're busy destroying at the moment, to some extent, through ocean acidification. I thought we'd get to that very briefly in the end of the time. Okay, so how do we reconstruct vanished oceans? Okay, we compile all sorts of geological and geophysical data from the crust that's preserved in the oceans today, from the continents as well. There's lots of telltale signs of how ocean basins have evolved. For example, through rocks like the ones that I've shown from New Zealand that have been shoved on top of continents and that are there for us to map and investigate. And you can date these rocks and they tell us something about when an ocean adjacent to this continent once existed. So what's playing on the right-hand side was a little animation, how we've reconstructed the Pacific Ocean. That's a view of the Pacific here, Australia in the lower left, and North America in the upper right. And the colors that are being shown here are the age of the ocean floor. And so this is something that I pursued starting with my PhD trying to merge disparate observations from the ocean basins into a coherent map of the age of the ocean floor. And it turns out that that's the starting point for mapping the depth of the ocean floor and also reconstructing it. We also look at what's underneath the oceans. That's what's shown in the middle. We use seismic images of the deep mantle that tells us where now disappeared oceans, tectonic plates that have been subducted, that have been recycled back into the deep earth, where they are now. And that gives us clues as to where ocean basins were once located. Now that we have the plate tectonic theory, that also provides us with rules for how the world works. For example, plates have speed limits, just like cars on a highway, right? And so we know that they can't move faster than a certain limit based on the geodynamic driving forces. And ultimately, they're driven by the convection of the Earth's mantle underneath them, and the decay of radioactive elements and the loss of the primordial heat of the Earth that we're still in the process of losing. Okay, so we use a lot of geological and geophysical data to plate tectonic rules to reconstruct the oceans. So what's shown here is again the present-day distribution of the age of the ocean basins, where the red colors denote the youngest ocean crust, and the bluish colors the oldest ocean floor. The oldest ocean floor that you find today is in a triangular-shaped region in the Western Pacific that you see on the right-hand side of this map. And it's about Jurassic in age, so Jurassic being the time that dinosaurs still roamed the Earth. And so sadly for us, we don't have much ocean floor preserved that's older than that. And so if we want to go beyond the Jurassic, beyond say 170, 180 million years, we have to use more indirect evidence and the rules of plate tectonics to figure out where now disappeared ocean basins might have existed. Right? And so what we're playing here now is an animation that goes back in time and that winds plate tectonics back in time and recreates the age distribution of ocean basins that are no longer there. I can't get into all the details on how we've done this. This is a relatively recent development that we are able to reconstruct the world in this fashion all the way back to 1 billion years ago. And the initial paper that was authored was led by an ex-PhD student of mine named Müller. There's 500 references and probably thousands of other papers that were indirectly referenced through those papers. And that's this giant body of knowledge, geology and geophysics, that has actually made its way into these reconstructions that were gradually and painstakingly carried out over years. Right? And so we don't really recognize the world anymore now. So we've arrived at a billion years ago, and the world has no longer any resemblance to what it is today. Right? And so what we're going to do now, right, we're going to go forward in time. We're going to go on a little journey through geological time, and very slowly to have a look, what the world looked like, what have we learned in the process. And then towards the end of the talk, I'm going to get into some applications of why this is useful, what drives us wanting to reconstruct the ocean basins. So this is what the world might have looked like. This is a model, of course, a billion years ago. Most of the continental fragments are assembled in one place, and there's a new supercontinent that was called Rodinia. And Rodinia is a word that's derived from Russian. It means something like the motherland or the birthplace of all present-day continents. Actually, we now know that an even older giant continent, a supercontinent, has existed before this one, so it's not actually the mother of all continents, but never mind that. And so we also have an ocean basin called the Mirovia Ocean that surrounded this giant continental mass. It didn't include all continents. There were some outliers. You see India, the now in existence here, close to the equator, and so did Siberia. That was only very loosely connected to this giant Rodinia continent. And so we also have Madagascar floating around there in a relatively lonely fashion, and to the south Sahara. We're going to get back to West Australia in a minute. Now we're going forward in 100 billion year intervals for now. Right? So now we've actually assembled this Rodinia continent on the eastern side of our globe here. And we have the Neurovia Ocean. And so the colors in these maps denote the depth. So we have now applied the Slater curve to our age reconstructions of the ocean basins so that we can convert age to depth. And remember, this is a straightforward operation because mid-ocean ridges are young and shallow, abyssal plains are old and deep. And so obviously there's quite a bit of imagination, if you like, that has been used in reconstructing the detail of what the ocean basins might have looked like that are now long gone. But we've used the available geological data in the rules of plate tectonics as best as we could to do this. And so so what do we see happening here? There's a new ocean basin that's forming called the Adamastor Ocean. That's actually a Portuguese interpretation of a Greek term that actually comes from a Portuguese novel. And Adamastor was supposed to represent all the obstacles and difficulties that the Portuguese navigators had to endure while exploring the ocean basins hundreds of years ago. And so the Adamastor Ocean is one of those untamable beasts, and you will see that it is quite a complicated evolution. And so going forward in time, India has now heavily moved from the equator very close to the North Pole. All the continental bits and pieces attached to India look so large just because of map distortion. And this so-called Robinson projection. And so we can take these shapes very close to the pole too seriously. But it's otherwise a handy way to display the whole globe. So that's why we stick to this projection, which has been very popular with the National Geographic for many decades for the same reason. So we have, now it turns out Rodinia, our supercontinent, is actually about to break apart. Siberia is soon going to go on its own journey. So we have the two pieces of Africa, Congo and Sahara on the lower left there, and Madagascar is still floating around in the middle. Right? So now, 700 million years ago, Siberia is still in the process of separating itself away from Rodinia, and we have an assemblage of three continents north of the Kalahari, that's still part of Rodinia there. So that's Antarctica, South Australia, North Australia, and North China, which form a curious assemblage at this time. And so they're actually on the path of converging with India right now. And so it's interesting to look at these worlds that have so little in common with the worlds that we're used to. But one other curious aspect of these early maps of the world is that the separation of Western Australia from the rest of Australia. And so the different cratons that now make up the core of Australia hadn't yet joined up. Right? So you see North and South Australia there between Antarctica and North China on the upper right. Whereas West Australia is in a different hemisphere now. Many of you might know that there's a bit of history to the secession of Western Australia. And so just to recap, in 1933, there was an effort carried out to secede, and over 70% of West Australians voted for separation, and they made they submitted a petition to the British Parliament. But sadly for Western Australia, the British Parliament decided that they didn't have the power to allow WA to secede. And so very sadly for them, they had to remain as part of the rest of Australia. And so one might argue that they were about 700 million years too late. If they had only lived at this time, they would have had their separate existence that they so yearned for. However, so this is actually, I dug these out, in fact, from the UNSW website, as it turns out. So this was the meeting of the Dominion League for the secession movement in 1934. There's some grim chatties holding the newly designed Australian flag on the upper right. Now, unfortunately, for them, perhaps even 700 million years too late, life in the Neo-Proterozoic would have probably not been very cozy for them. At the time, the Earth was inhabited by bacteria. There was no land vegetation, and there was very little oxygen to breathe. That came much later. So after all, they probably wouldn't have been too happy living in this kind of landscape, even though it was far away from the rest of Australia. So that was a little excursion here for us. So going back to our paleobathymetric reconstructions. So now we have arrived 600 million years ago, where our continental assemblage and the oceans, our network of mid-ocean ridges and abyssal plains is still changing. The Morovia Ocean has actually now morphed into something that could be called the Proto-Pacific Ocean. The Pacific Ocean that we have now is actually probably the longest lived ocean basin that we have. In its core, it's been around for 600 million years, even though the crust that existed at this time has all now been disappeared into the deep mantle. So we have Proto-Africa forming in the southern hemisphere there. We have the Almastra Ocean is still around after some complicated opening and closing journey. As we've now reached the halfway point between 1 billion years ago and the present at 500 million years ago. And so what we're seeing now, we're actually seeing Gondwana land assembling in the southern hemisphere. And so Gondwana land was nearly a supercontinent. It's not referred to as a supercontinent usually because there were too many little bits and pieces that weren't actually joined up with Gondwana land. So we had Laurentia, so it's North America, Greenland, and Siberia, and Baltica, leading a separate existence. And we also had an ocean opening up between those continents in the west, Laurentia, Siberia, Baltica, and western Gondwana land. And that's called the Iapetus Ocean. And you see another ocean basin on the right hand in the middle, that's called the Rheic Ocean. So there's a bit of a story behind those names. You might know that the Atlantic Ocean is named after the Greek god Atlantis. Now, the Iapetus Ocean was often viewed as a precursor of the Atlantic because where the Atlantic formed, essentially what happened in the Atlantic, the Iapetus Ocean formed, it closed, and then later a new ocean basin opened in the same place. Right? And so, of course, Iapetus in Greek mythology was the father of Atlantis, and Rhea was the sister of Iapetus. And because Iapetus and Rhea, the Rheic Ocean, were both precursors to the Atlantic, hence these names for these old ocean basins. And so now, here we have two perfectly realistic pictures of Iapetus and Rhea taken from the aptly named Gods and Demons Wiki. So if you ever want to find out what these deities might have looked like, this is the place to go. Okay. 400 million years ago. So now we still have Gondwana land assembled in the southern hemisphere. There's Low Russia, there's an amalgamation of North America, Greenland, and parts of Russia, excluding Siberia, leading a separate existence. There's the Rheic Ocean that's growing. The Iapetus Ocean is now gone, and hence the amalgamation of Low Russia. Actually in between there before, between these bits and pieces that have now formed one landmass. And so on the northeastern side of this image, we have, so SC and NC stands for South China and North China. So they actually had a separate existence for a long time until they finally became all part of Eastern Asia. And so we'll see as we now move forward in time to 300 MA. So now, finally, most of these different bits and pieces have joined up. The Rheic Ocean has been destroyed by subduction, and destruction of the ocean floor that formed it. And so we have formed Pangea, which is again derived from a Greek word meaning all land. And so nearly all continents were combined in Pangea, except for South China, North China, and there's actually Madagascar floating around as well, west and South China, and some other little bits and pieces that later became part of Asia. And so 300 million years is an interesting time, because that's actually the onset of the Permian period. And all those of you who have spent time walking along beaches of the Illawarra coastline, where I have spent much of the time during COVID, you'll be familiar with rocks that are exposed there that were deposited during the Permian period. So the coastline there is entirely made up of rocks that are older than 250 million years. So this is what the world might have looked like at this time. So we had Pangea assembled, but because so much of Pangea, in fact the part of Gondwana land that formed the southern part of Pangea, was very close to the pole that presented the perfect conditions for a glaciation to form. So we had a large ice cap at this time. In fact, this glaciation started during the Carboniferous period that preceded the Permian. So it's often referred to as the Permo-Carboniferous glaciation. And so there's a picture on the right-hand side that's an artist's depiction of what the Permian landscape around Sydney might have looked like. So at this time, this would have been a region shaken by earthquakes very frequently, because there was a huge subduction zone that had been active for hundreds of millions of years, but there was old cold crust being recycled underneath Australia, and it would have been very similar to what's now along the Andes, for example, what the tectonic regime is like. And so we had a Cordillera mountain chain that was likely snow covered for at least part of the year. You see ice blocks floating in water down there on the lower right. And so sometime towards the end of the Permian period, this glaciation came to an end. And this final stage of the glaciation is actually particularly well recorded in the rocks that you find along the lower beaches. So here's a photo I took at Bombo Beach at Pheasants Point. And what you see here is the brown volcanic sandstone. So all the sandstone that was deposited in shallow coastal area at the time was derived from volcanoes. The area was full of volcanoes at the time. It's subduction-related volcanoes, very similar to the volcanic and magmatic activity you find in the Andes today. But one of the curious things that you find here, and this is where this finger is pointing to in this photo, is a large pebble that seems to be embedded in this very fine-grained matrix. And one might ask, well, how do these pebbles get there? This is a shallow, marine, sandy sediment. You wouldn't normally find large pebbles in it, right? It turns out that there are whole horizons of pebbles, and they owe their existence to melting icebergs. So when the edge of an ice sheet gradually melts, that's of course what's happening along the edge of the Arctic ice at the moment, thanks to human-induced global warming. These icebergs, they drift out into the open ocean, and they melt, and they're all full of debris that have been scraped off the continent. And this debris is then released and dumped onto the seabed. And that's how it got there. And you find this, once you develop an eye for this, and I should also mention that there's quite a lot of fossilized wood in these sediments as well. So if you're an avid collector of rocks and fossils, then I definitely recommend checking out some of those at the lower beaches. There's some beautiful pieces of fossilized wood. I have a large collection, as you can imagine. And so here's a photo from Blackhead and Jarawa. And so it's again the layer of these glacial drop stones that are a testament to melting ice and drifting melting icebergs at the time. Right? And you find these layers even as far as Mariah Island, Tasmania. Has anybody been to Mariah Island? Yes, I see a few hands going up. Very, very good. It's a wonderful place. And if you're interested in geology, it's a great place to have a look at not only these dropstones, but also fossils. And so, for example, what's shown here, there are two horizons, and you can see that there are these horizons that have these large pebbles embedded in them. But you also see these shapes of fossils. Right? This is actually a bivalve called Dietmar. So it's very typical for life in the late Permian. And so you find some beautiful examples of these large bivalve shells in these horizons on Maria Island. And sure, yeah, so that's the end of the Permo-Carboniferous Ice Age. Now we're going back to our reconstructions of the world here. So 200 million years ago, that's actually the time that Pangea started disintegrating. It was stable for about 100 million years, and that was about it. But we see something else here. We see a new ocean basin that wasn't there before, that's northeast of Pangea. It's between Gondwanaland and China and the rest of Eastern Europe. So China started forming now, so the North and South China and various other bits and pieces have started amalgamating. And there's an ocean called the Tethys Ocean. And that ocean went through various phases of evolution until the northward motion of India and Australia away from Gondwanaland destroyed all the ocean floor in the Tethys between Gondwanaland and Eurasia, east of Africa, and the Indian Ocean as we know it today finally formed. And that's how we arrived in the world that we're familiar with today. And so now I'm going to show you an animation. And so I should really stress that this is the first time, it's a relatively recent development that we've been able to create this continuous depiction of the evolution of the ocean basins over the last billion years, right? And so you see this dance of the continents and the appearance and the maturing of new mid-ocean ridges, the formation of new abyssal plains. There's a new mid-ocean ridge system appearing, and later it becomes extinct, and all these mid-ocean ridge crests subside and ultimately turn into abyssal plains. But mid-ocean ridges can also become subducted. They hit the subduction zone and are being recycled. That actually happens near the so-called Chile triple junction today. Just offshore Chile, there's a mid-ocean ridge that's being shoved underneath the Andes, and it's disappearing. And so we've seen this happen again and again in the geological past here. When the reconstruction underlying this was first published, it was actually written up in the New York Times and in many other places around the world. And viewers developed a real fascination with this, and you got all these messages saying, I can watch this over and over again. And there's so many things happening, and it's true. And it takes you a while to actually find a way to recognize which bits are which and what you're actually looking at back in time. And so let's actually move on to applications of these reconstructions. So I just want to briefly touch on three particular applications here. Long-term sea level change, the deep carbon cycle, and understanding the evolution of marine biodiversity. Right? So first, to static sea level. Use the sea as a word for global sea level. It's the worldwide sea level regime and its fluctuations. It's the kind of thing that will happen as we start melting the Antarctic ice. Static sea level will go up, no doubt. And we need to be prepared for that to happen, I'm afraid. And so what our interest was and is to reconstruct these sea level fluctuations over much longer time periods than just human time periods. And what is particularly interesting is that we see these large sea level fluctuations in the geological record long before we had an ice age. So the Antarctic ice cap that we are familiar with today started forming initially 35 million years ago. And there was no inland ice on Earth before it was in Permian that existed then. But between 250 million years ago and 35, there was none. Right? So what's also an interesting thought in this context is that if you look at the entire evolution of the Earth, having ice ages in the sense of having any inland ice at all is actually an anomaly. Like the normal state of the Earth, if you like, geologically speaking, is having no inland ice at all. Right? And so, as a geologist, I might argue we are now on the path of re-establishing normality on Earth. Right? But unfortunately, humans having populated all the coastal regions, certainly humans are not going to be so happy with this outcome. Sadly. So if you look at long-term sea level and coastline change, so here we go, here we have 4 published maps starting 150 million years ago on the upper left and going to the present. So the Earth has gone through very distinct phases. We had a relatively low sea level when Pangea existed. Pangea was high and dry mostly. But then when Pangea started falling apart, right, sea level started rising, and we had really high sea level in the late Cretaceous period when dinosaurs were still roaming the continents. And that's shown on the upper left. So many parts of the continents were flooded at the time. Large parts of North America, Eurasia, even Africa, and parts of South America. And this was still the case 50 million years ago, but then at the present, the continents are mostly high and dry. This mostly doesn't have anything to do with inland ice and water being tied up in it, right? And so there's a number of drivers of sea level change, and I'm not going to bore you with all the different mechanisms that play a role there, because temperature plays a role in thermal expansion. And what I actually want to focus on is what's shown on the upper right, changes in seafloor spreading rates and the nature of seafloor spreading, meaning how long were the mid-ocean ridges, right? And this is how it works. So there's 2 simple pictures shown here. And it turns out seafloor spreading rates of mid-ocean ridge systems can drive sea level change. Because if you make the mid-ocean ridge system longer, if you create new mid-ocean ridges that weren't there before, right? Of course they're shallow, right? And what they do is they end up replacing abyssal ocean floor. And so that means you are reducing the volume of the ocean basins. There's less space for the water, right? And the same happens if you accelerate seafloor spreading, if you make it faster, if you increase the speed of this giant conveyor belt, right? You're creating more young and more shallow ocean floor. Right? And again, you're reducing the space available for the water in this giant bathtub, if you like. And so if we now just look at changes in if we look at and this didn't really work the way it was supposed to work. I think there's something that got screwed up here. That's okay. We can probably live with this. So what happened as Pangea broke apart? Right? There were all these new mid-ocean ridges that formed in the Atlantic and the Indian Ocean that didn't exist before, and there were also even in the Pacific many new mid-ocean ridges formed. Right? And they simply reduced the volume of the ocean basins, and that's the explanation for why sea level was so high in Cretaceous. It's a simplified version. There are many other processes that also play a role, but that's one of the fundamental drivers. So I just want to say a few words about the global carbon cycle. We see quite a bit written up about carbon as we're pumping CO2 in the atmosphere at the moment that we don't necessarily need there, and how the ocean absorbs quite a lot of that driving ocean acidification. Now, again, we can use the geological record to reconstruct how the deep sea carbonate sink has evolved through time. So what I'm showing here, it's actually a picture of the Indian Ocean. We see Australia on the right-hand side, and there's Madagascar and Somalia visible, just on the left-hand side. And it's a northward view towards India and Indonesia. And it's a view of the seafloor. We see the fabric of the seafloor. And the colors actually stand for the type of sediment that's covering the seafloor. Now the blue colors are carbonate sediments. And these carbonate sediments, they're created by planktonic organisms. They're tiny little critters that live in the sunlit surface water of the ocean. And they're either phytoplankton, they live on photosynthesis, or they're zooplankton, so they're a bit bigger and they eat the phytoplankton. And so they either make skeletons or shells out of carbonate material. And And when they die, these shells fall to the sea floor, and that's often referred to as marine snow. And so, but not everything in the ocean is blue here. Right? So there are some areas that are brown, but let's not talk about the other colors for now. So the brown is actually a bit of clay. And so it turns out the deepest parts of the oceans, the abyssal plains, they are covered just by clay. And only the shallower parts are shallower, meaning shallower than 3.5 kilometers depth. They're covered by carbonate. And why is that? Okay, it's not that there's no carbonate being produced in the water column in those places. It's got to do with the chemistry of CO2 in water. So it turns out that as pressure increases in water, it's easier to dissolve CO2. Right? And so that means that the marine snow, or these tiny little fragments of shells and skeletons that fall through the water column, they are more readily dissolved at greater depths. And at some point, at a depth that's called the calcite compensation depth, they are no more. They are entirely dissolved. Right? Now, this also depends on temperature and the acidity of the water, so the CO2 concentration in the water. Right? Hence, ocean acidification makes a difference for this as well. So the little diagram that's shown here in the slide illustrates this. There's the marine snow raining down, right? And there's dissolution going on in a certain depth band, and then all the carbonate is gone, and you only deposit carbonate when the ocean depth is relatively shallow, and once you exceed this depth, there's only this yellow horizon here, the deep sea clay being deposited. The reason why this is important to us is that the carbonate deposits in the oceans are in fact the world's largest carbon storage reservoir. That's actually where the vast bulk of all carbon is being stored. Right? And there's a long chain of reactions that transports material from continents to the oceans and through erosion and to make this happen. And so what we were interested in, trying to experiment how this oceanic carbonate storage has changed through time. And this is what we've done here. This is an effort that was led by my colleague Adriana Dulkiewicz a few years ago. And the colors here show the thickness of the carbonate sediments in the ocean. So when the colors are blue, there's hardly any carbonate sediment there. And the redder the colors become, the thicker the carbonates in the oceans. And this video was supposed to go to 0, but somehow it stopped. That's okay. And so what you see here is that the world becomes more and more orange through time, right? Meaning that there's more and more carbonates being deposited on the seafloor. And so our work has shown that the oceans didn't used to be the largest carbon sink, but they are now. They've become the largest sink for carbon in the last 30-35 million years. In fact, during the time when an ice age developed, and during the time when we've destroyed many shallow seas on the continents that used to be the perfect habitats for carbonate-producing organisms, and they were all forced to migrate out into the open ocean, and the remains have now been deposited in the deep sea. So understanding these sorts of cycles are also important for understanding what role carbon and CO2 plays in climate change through time. The last thing that I want to mention is marine biodiversity. And so I was lucky enough to be part of a team that worked on combining our paleobathymetry maps with a paleoclimate and biodiversity model to better understand biodiversity evolution during the entire time period when complex life evolved. So that's the last 550 million years. And so that paper actually made it onto the cover of Nature. We're very happy with that. That's what's portrayed on the right-hand side there. And so what the question that we were asking is, so what are the most important factors for driving marine biodiversity? So it turns out that the graph on the lower left-hand side that's shown there, the curve illustrates the evolution of biodiversity from about 550 million years ago on the left to the present day on the right. And so there's a sort of a complex curve initially where biodiversity increased, but then it decreased again. And we tried to find out what the reason for that was. And the record, the paleontological record, is too incomplete just to derive the answer from the observations. You actually need to create a computer model to understand it. And so this is what we did. We combined our maps reconstructing the oceans with this model, and that's what's shown, that's playing on the left-hand side. But the colors here, what they actually display is the model biodiversity. And what you see here is that biodiversity tends to develop in shallow marine areas. These are the shallow, warm areas where biodiversity most readily evolves. And if we actually look at this again and look at the graph that's evolving there, so that's biodiversity. The gray bars that are evolving on the graph are extinctions. They're major extinctions. And so we had a complex tectonic evolution, all these small plates moving around between 500 and 200 million years ago. And the consequence of this evolution was that these nice shallow water environments that are good for biodiversification, they never lasted. And so they only existed for relatively short periods of time because they were destroyed by tectonic processes. And the extinctions also helped with reducing biodiversity again. Right? So it turns out that most of the marine biodiversity that we have today was developed over the last 100 million years. Right? And you see on this map that we're showing there, the yellow and orange spots, they are all the shallow seas where most of the current marine biodiversity can be found. And so that's essentially the Caribbean, that's the Mediterranean, and there's shallow Southeast Asian seas as well. And so this model helped understand the key factors, which is having warm, nutrient-rich water persisting for a long period of time in the same place without interruption. Now, if the current trends continue, then the projected diversity loss in the oceans may take millions of years to recover. So that was the take-home message from this Nature paper. And so this is my last slide. So my conclusions are that paleobathymetry reconstructions are a useful tool to understand the evolution of life, the carbon cycle, and long-term sea level, and it turns out a few other things as well. So on the right-hand side, my last video shows the opening of the Atlantic Ocean, but all the little colored dots that are shown here along the Andes and along the Rocky Mountains in North America, they are actually copper deposits. And so copper is, of course, a critical metal that is that we need for the future green energy revolution. It's partly already here, but it's not quite sufficient just yet. And so the amount of copper that we will need is really quite mind-boggling. I'm not going to get into this here. It turns out that these paleobathymetry maps can also be used to better understand the tectonic environments where these copper deposits form along large mountain chains. And this is because of bathymetric obstacles that when they get subducted, they cause the formation of the overall plate and differential fluids that can rise up and form these deposits. So this is actually something that my team is mostly focusing our work on at the moment. And so that's it. Thanks very much for listening. And if you are on social media, we're on Facebook and Twitter, and feel free to follow us. Thank you.